Hello everybody, getting ready to do lesson 2.6 part 1 of pre-calculus math today. Email me here for other materials, note-taking guides, PowerPoints, tutoring. 2.6 part 1, rational functions and asymptotes. You had 2 points of note-taking in this lesson here. And then you got 44 points of classwork to do today. Teachers, today's bell work is a review. Students, write the general form of the equation of the line that passes through these 2 points here. Give your students about 6 minutes to do that. Okay, welcome back for our solutions for today's bell work. And we have these 2 points here, 3, 2, and 0, negative 1. So the general form of an equation here is y1 minus y2. Then we need the slope here. Then we have x1 minus x2 here. Then when we get through with our calculations here, we have this equals here 1 times quantity x minus 3. And then when we do our solving for y, we move this over here. We get y equals x minus 1. Or we can get this configuration here if you wish, to make it 0, to put it into your calculator. I wouldn't do that. That wouldn't go into your calculator. But this would be your general form of the equation here. And then down here, same thing here, y1 minus y2. And then figure your slope times x1 minus x2 here. And then once we do our arithmetic through here, 10y plus 10 equals 6x plus 36. We get 3x plus 5y plus 13. I mean, we could, by the time we move this over here, and divide through by negative 10, you would get your general form there. But in this situation here, this is another way of putting it, making it equal to 0. Okay, into our first slide here, Introduction to Rational Functions. A rational function can be written in the form like this, where nx and dx are polynomials and dx is not the zero polynomial. In general, the domain of a rational function of x includes all real numbers except x values that make the denominator 0. So we cannot have 0 in our denominator. Much of the discussion of rational functions will focus on their graphical behavior near these x values. So let's take a look at a rational function, finding the domain of a rational function, and find the domain of f of x equals 1 over x, and discuss the behavior of f near excluded x values. So this is f of x equals 1 over x. This would be the graph of that. And because the denominator is 0 when x equals 0, the domain of f is all reals except where x equals 0. To determine the behavior of f near this excluded value, evaluate f of x to the left and right of x equals 0 as indicated by the following tables here. So as x goes to 0 from the left, we get that. And f of x will go to the negative infinity. So as it goes closer to 0, f of x goes to negative infinity. And then as x approaches 0 from the right, f of x grows to positive infinity here. So as x approaches 0 from the left, f of x decreases without bound. And then from the right, f of x increases without bounds. So you have this situation here and then that situation here for f of x equals 1 over x. And then f would not be continuous here. Just by looking at your graph, you could tell that. So let's go into a guided practice here. Find the domain of the function, of this function here. What is the domain of that function? Complete each table. So we have a table here for this function. Complete the table. And then discuss the behavior of f near any x value. So that's our task here for this function here. So to do that, domain is all x except 1. So where x equals 1, there is no continuation of your function. And then as f approaches negative infinity from the left of 1 and infinity from the right of 1. So from the left it goes to negative infinity, and from the right it goes to positive infinity for the values. Vertical and horizontal asymptotes. In example 1, the behavior of f near x equals 0 is denoted as follows. So as f of x approaches negative infinity, as x goes to 0 from the negative side of the number line, which means, what does that mean? F of x decreases as x approaches 0 from the left, and as f of x approaches infinity, as x approaches 0 from the positive side. So increases without bound is as x approaches 0. That's another way of putting that graph behavior into language. The line x equals 0 is a vertical asymptote of the graph. Here's your x equals 0 is right here, is your y axis of the graph is shown. And the vertical asymptote is the y-axis. The horizontal asymptote would be the x-axis here. So as the graph of f has a horizontal asymptote, the line y equals 0, or the x-axis is y equals 0. This means that the values of f of x equals 1 divided by x approach 0 as x increases or decreases without bound. So you have this situation here. As it approaches 0, your graph goes in different directions as it approaches 0 from different directions. So as f of x approaches 0, as x goes to negative infinity, so f of x goes, here we go through it again. So as it approaches 0, as x goes to negative infinity here, which is here, as f of x approaches 0, as x decreases without bound, and then f of x approaches 0 as x increases without bound. So you have this dynamic here, depending upon which direction the graph approaches 0. Definition of vertical and horizontal asymptotes. The line x equals a is a vertical asymptote of the graph of f when f of x approaches infinity or f of x approaches negative infinity. As x goes to a, either from the right or from the left. The line y equals b is a horizontal asymptote of the graph of f when f of x approaches b. So as x approaches a from right or left, the line y equals b is a horizontal asymptote of the graph when f of x approaches b. As x approaches infinity or x approaches negative infinity. So you have situations here where the graph will manifest itself as x goes to positive infinity or negative infinity. Well, let's see an example of that. So vertical and horizontal asymptotes of graphs of three rational functions. So for f of x equals 2x plus 1 over x plus 1, we have this situation here where it goes to positive infinity as it approaches 0, or rather as it approaches negative 1. And then this side of your graph approaches negative infinity as it approaches negative 1 from the positive side of the number line. And then your horizontal asymptote here will be y equals 2. And then your vertical asymptote is x equals negative 1. And then this one here, 4 over x squared plus 1. You have a horizontal asymptote here of y equals 0. And you have no vertical asymptote here. So the graphs of f of x equals 1 over x and f of x equals 2x plus 1 over x plus 1 are called hyperbolas. There's a new definition there, vocabulary. And then in this situation here, we have a vertical asymptote at x equals 1, and then a horizontal asymptote here at y equals 0. For this function here, 2 over the quantity x minus 1 squared. So you get this situation here. Vertical, horizontal asymptotes, rational function. Rational function like this, n of x over d of x in our usual standard form of a polynomial. The only thing is now we have a numerator and denominator where they have no common factors. The graph of f has vertical asymptotes at the zeros of d of x. So if they have no common factors, then we have vertical asymptotes here at the zeros of d and x. So we have to find our zeros over denominator. That will be your vertical asymptotes. And then the graph of f has at most one horizontal asymptote determined by comparing the degrees of n of x and d of x. So if n is less than m, in this case if n is less than m, then the graph of f has the line y equals 0 as a horizontal asymptote. So if the degree of n is less than the degree of m, then y equals 0 will be your horizontal asymptote. And then the same thing here, if b equals m, if n equals m, then the graph of f has the line y equals a to the n b over m as a horizontal asymptote, and where a to the n is the leading coefficient. Here's our leading coefficient of the numerator, and b is the leading coefficient of the denominator. So a horizontal asymptote when n equals m would be the ratio of a to the nth over b to the nth. If n is greater than m, then the graph of has no horizontal asymptote. Let's get into an example now of that, finding vertical and horizontal asymptotes of this situation here. So for this rational function, the degree of the numerator is less than the degree of the denominator. Here the degree is 2 in the denominator, and the numerator is 1. So the graph has a line y equals 0 by default, has a y equals 0 as a horizontal asymptote. To find any vertical asymptotes, set the denominator equal to 0, set this equal to 0, and solve the resulting equation for x. So 3x squared plus 1 equals 0, set the denominator equal to 0. What do we come up with for that little situation there? This equation has no real zero, so you can conclude that the graph has no vertical asymptotes. It has no vertical asymptotes here. A horizontal asymptote would be y equals 0 here. So this graph will go like this, using the x-axis as a asymptote, and on this side it will go like this, using x as an asymptote for there as well. Another situation, 2x squared over x squared minus 1. For this rational function, the degree of the numerator is equal to the degree of the denominator. So the leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 1. Here's 1 and 2. So the graph has the line y equals 2 as a horizontal asymptote. To find any vertical asymptote, set the denominator equal to 0 and solve the resulting equation for x. So x squared minus 1, set the denominator equal to 0. So what do we come up with here? Here's our horizontal asymptote. What is our, if we have any vertical asymptote? So you solve this for 0. We factor this down. It's the difference of a square. So we have x equals -1 as one vertical asymptote, and x equals 1 as our other asymptote. So in this case here, x equals 1 and x equals -1 as vertical asymptotes. So here are your asymptotes here. So and then here's your actual graph of this function here, 2x squared over x squared minus 1. So we have a horizontal here at y equals 2. Then we have 2 verticals here. And then we have our function coming up there this way between our asymptotes, and then going like this up here. And that is how that is looking there. Then we go into our guided practice here. So how do we solve for these here? Vertical asymptote x equals 0, horizontal asymptote y equals 0, or the x-axis. And then down here, vertical asymptote x equals 2, horizontal asymptote equals y equals 0 in that situation. And that is your lesson for the day. Email me here for questions and materials. Thank you very much.